So after dielectric spectroscopy, we will now discover a few other non-destructive diagnostic techniques which can be used in order to determine the condition of insulation. The first technique that we shall discuss is that of the recovery voltage measurement. In this, we have the sample here, and across the sample, a DC charging voltage is applied for a specific time. So for example, as you can see here, for time Tc, DC voltage is applied across the sample. After that, the supply is removed and the sample is short-circuited. We have a voltmeter here which registers the voltage during the short circuit conditions. Usually we will short circuit for a smaller time, so maybe Tc by 2, and after that we shall record the recovery voltage for a predetermined time. So as we can see, we charge the sample up to Tc, and then we let the sample discharge, and after Tc by 2 time has passed, we measure the return voltage. We measure the recovery voltage, which is also called the return voltage. Now, the parameters are supposed to be related to the moisture content. So in this way, we can figure out where there has been any significant moisture ingress inside the dielectric material. We know how moisture can affect the material, and we would like to know whether there has been a lot of moisture ingress in the material. The parameters that are dependent on the moisture content are the maximum recovery voltage. So if this is the recovery voltage that is measured after time Tc by 2, what is the peak value of the maximum peak value of the recovery voltage, or what is the maximum voltage that is observed, and what is the time of occurrence of Vm? So the time to Vm is important, and the slope alpha of the initial voltage rise. So these are the three parameters which are of significance in comparing the moisture content or similar degradation in various samples. The procedure will have to be repeated for many values of charging time, and the critical time to maximum voltage is determined, and the slope of the slope to Vm is also registered. So for example, here we have some examples of possible variations of the characteristics with apparent moisture content in oil impregnated paper. So all these three plots refer to oil impregnated paper, but they have different quantities of moisture ingress in them. This has 2%, this has 3%, and this has 4%. As we can see, the maximum values are not very different, only slightly different. However, the slopes are considerably different, and the time to maximum voltage is quite different. For example, the time to maximum voltage is very high for 4% moisture ingress, but much less for much higher for 2% moisture ingress. So in this way, we will be able to differentiate between the samples. The range of charging times is from 0.02 seconds to 10,000 seconds, and comparisons will be made for a fixed Tc for the time to Vm. Apart from this, we may also perform resistivity or conductivity measurements. When we are talking about resistivity or conductivity measurements, we are essentially talking about the DC conductivity of the sample. Now, we have discussed this briefly before, but let us look at this electrode assembly more clearly. In case of resistivity measurements, the electrode configuration is specified by the IEC standards, and what we usually utilize is not a two electrode system. That is, we don't have 2 points, potential applied between 2 points simply and just measure the voltage and current between them. Instead, we have a 3 electrode configuration. Let us look at this 3 electrode configuration. We have a ring electrode which is used. The ring electrode sits outside a central electrode. So this is the guarded electrode, and the ring electrode outside is the guard electrode. These 2 electrodes are on one side of the sample. On the other side, you have a simple cylindrical sample. So on the top, as you can see, you have a simple cylindrical sample. This is solid in nature. And on the bottom, we have the guarded electrode and then the ring electrode guarding them. This is a photograph of the kind of electrode that is used. This is the outside. We have the annular electrode, which is the guard electrode. Inside, we have the guarded electrode. And then below, we have the solid cylindrical normal electrode, and between these two electrode assembly we put the white sample. We also make sure that the electrode assembly makes good contacts with the dielectric material. These are some of the standard specifications for the diameters of the guard and unguarded electrodes, which are taken from the IEC standards. Now, the reason that we need to use the 3-electrode system rather than a 2-electrode system is because in case of dielectrics, the surface resistivity of a material is comparable to the volume resistivity. So we can measure the surface resistivity separately, we can measure the volume resistivity separately. And we need to separate out these resistivities. If we are looking at the material parameters or material characteristics, we need to characterize the material, we need to look at the volume resistivity. Otherwise, the surface resistivity is a function of not only the material, but also the ambient around it, also the surface conditions. So depending upon what we are looking at, we might need to measure the surface resistivity, or we may need to measure the volume resistivity. With the same 3-electrode assembly, both resistivities can be measured, but the connections would be different. So let us look at what the connections would look like. Surface resistivity, when we are measuring, we put the sample here. The the high voltage electrode is here, and the guarded electrode and the guard electrode are sitting here. The guarded electrode is connected to the high voltage potential. So this is your supply. The DC voltage is applied across this, and the high voltage supply goes to the ring electrode, and through a ammeter, we have the other connection to the sample. On the other hand, the same potential that is taken to the sample here is also taken to the guard electrode, which means that both these electrodes, which are on two sides of the sample, are at the same potential. So strictly speaking, there is no potential difference across the volume of the sample, and no current should flow through the sample. So volume conduction is eliminated. This guard electrode and the guarded electrode are at different potentials, the high voltage and the low voltage ends of the source, and therefore there should be, depending upon the potential difference between the two, there should be a current flowing from the ring electrode to the inner electrode. And this will be governed by the surface resistivity of the material. So what we measure with the picoammeter, we use a picoammeter because these currents can be very small, and we also have to be very careful while making these measurements, because even if you have any kind of disturbance, even due to movement in the vicinity of the sample, you will register fluctuations in the measurement. So we use a picoammeter to measure the current that is flowing through the circuit, and the current that will be flowing through the circuit in this configuration will depend upon the surface resistance of the material in between these 2 points. There is no current flowing through the volume of the material. Surface resistivity therefore can be calculated as rho s is equal to Ks into R. R is the surface resistance in ohms, which is of course the voltage to current ratio. Ks is a factor which is dependent on the configuration. G is the distance between the two, and P is the effective parameter, the size of the electrode. So using this configuration, the surface resistivity can be measured from the current voltage ratio that is measured by the picoammeter and the known voltage difference between the two. So this is how to measure the surface resistivity. This is how we measure the surface resistivity with a 3-electrode system. The same 3-electrode system can be used for measurement of volume resistivity of the same sample. However, the connections need to change. We now need a potential difference across the sample, and we need no potential difference along the surface, so we need to eliminate the surface currents. So what we do here is the high voltage lead is the high voltage end of the supply is connected to the supply here, to the sample on the bottom electrode or on the solid electrode, and the low voltage side is connected to the guard electrode as well as to the guarded electrode. So as you can see, on the bottom of the sample, the guard electrode and the guarded electrode are both at the same potential, and therefore there should not be any currents flowing along the surface of the sample between the two electrodes. So the current that would flow through the picoammeter would be the current that is flowing through the volume of the sample, because across the sample thickness you have a potential difference, the potential difference which is established by the high voltage source, and the current flows through the picoammeter, and from this the volume resistivity can be measured. According to ASTM calculations for volume resistivity, this can be calculated as rho v equal to kV R by T. R is the volume resistance here in ohms as opposed to the surface resistance in the previous slide. T, the average thickness of the sample. Remember, a sample may not be uniformly thick, so you might have to take the thickness measurements over various points and take an average of that, because the thickness of the sample will decide the resistance that you have in the direction of the flow of current. kV is the effective area of the guarded electrode for the particular electrode arrangement that is employed, and kV can be calculated as pi d naught by 2 whole square, d naught being the diameter of the outer diameter of the electrode. So using the 3 electrode configurations, we can eliminate the surface currents and the volume currents. Most of the time we are interested in the volume resistivity, because that is a property which is characteristic to the material. So if your sample is degraded, if it is aged, if there are lots of voids, if there is a lot of moisture, this should reflect in the resistivity measurements. So this is how we do the current measurements. So initially we have the test object and we connect the voltage. This is the test object is connected with 3 electrode configuration, and you connect the voltage supply and the picoammeter across the test object, apply a step voltage, and the current that flows is called the polarization current. What is the polarization? The current that flows on energization does not depend only on the conductivity of the material. There will also be a certain current that will flow in the material. There will also be a certain current which will be flowing through the material in order to establish the polarization mechanisms, and depending upon the kind of polarization mechanisms, this current will flow for a shorter time or a longer time. The polarization currents will continue to flow until and unless the polarization mechanisms are complete. So we don't really know a priori what would be the time for which polarization is required. We will establish a polarization time or an energization time depending upon the material in hand and depending upon our engineering and scientific judgment. So the polarization time should be sufficient for all the polarization mechanisms to be complete, so that the conduction current or the current through the test object reaches a steady state value. After that, so what we see is immediately on energization, a very high current flows, and then this current will settle down to a steady state value. So the initial current that flows goes on to establish the polarization mechanism. Now, as each of the polarization mechanisms are completed, so polarization is complete, the dipoles are created, and the dipoles are completely aligned in the direction of the field, then the current due to that polarization mechanism will stop, and you will be left with current which is needed to set up the slower polarization mechanisms. So depending upon what kind of slow polarization mechanisms are there, it will take a much longer time, but ultimately at a certain point the polarization currents will be eliminated and a steady state currents will flow. This is at steady state after all polarization mechanisms are complete. This current is expected to be merely due to the conduction, DC conductivity current. So if you measure if you energize a sample with a DC voltage, and if you wait for a sufficient amount of time such that all polarization is complete, the current that flows should be the DC conductivity current and can be used to measure DC conductivity. However, especially in polymers, this may require a very large time. If you have very large polymeric molecules, this polarization time that is required for steady state to be reached can be very large, especially if you have aged or degraded samples. Also, after a certain point, when you have only the very slow polarization mechanisms left, it is very difficult to figure out whether a steady state has been reached, because the reduction in current quantity might be very slow. So therefore, what we do is, after waiting for a sufficiently large polarization time, we depolarize the material, in which case we should open up this circuit. This red switch is opened up, and this red part, this IP ceases to flow. Instead, you have a flip switch such that now this switch is closed, so the test object is now short circuited. And because the test object is short circuited, there will be a current ID, or the depolarization current, which will flow in this blue loop. So this is shown here. This is the depolarization time. Now, typically, the time to depolarization should be ideally equal to the polarization time. So whatever time is required to fully polarize the material should also be the time that is required to fully depolarize the material, in the sense that once you remove the energy, once you remove the supply voltage, all the polarization mechanisms will be lost, in the sense that the dipoles will lose their alignment. They will cease to be aligned in the direction of the field. They will regain their random arrangement, and some of the dipoles, dipoles which are not permanent dipoles, but the induced dipoles, the dipoles in the material which have been induced due to the application of voltage, will lose their dipole property. So whatever we have done, whatever polarization mechanisms have come into play on energization, will now be released. So this is the depolarization current. The depolarization current would generally follow variation with time like this: A as a function of temperature, T to the power minus N, and a similar manner of depolarization, similar manner of decrease in current due to depolarization should also occur. So here again, at the instant of short circuit, a very high depolarization current begins to flow, and as the polarization mechanisms relax, as the material relaxes, the depolarization current dies out. Now so again here we would come to after we have waited a sufficient time for depolarization, what should happen is, in this case, after polarization is complete, there should be a substantial current flowing, and that current is the conduction current, which is slow because of the resistivity of the material. However, in short circuit conditions, ideally the steady state value should be 0. Sometimes there may not be, because we don't have any energization, so we don't have any potential difference to drive a current through the circuit. So ideally speaking, this current should go to 0. The depolarization current should go to 0. And the polarization time should be equal to the depolarization time. In fact, the polarization time and the depolarization time should be mirror images of each other. However, in reality, that does not happen. What happens is, you might have a very small residual current flowing even after waiting for long depolarization times. One, it could be because depolarization is not complete, and there are some very slow processes still going on, and you may have to wait for a very large number of days for this depolarization current to die out. That is a possibility. There might be other measurement errors or some other reasons for which a current might flow. So therefore, to err on the right side, to have more accurate measurements, what we consider is that we consider the polarization mechanism is completely reversible, so that the time we wait for the polarization current to reach a steady state. If we wait for a time t, then we also wait for a time t for the depolarization to be completed. And then we take a measure of the IP at time t and ID at time t. Time t after polarization. So IP is measured at time t after polarization, or after switching on of the supply. And then ID is measured at time t after short circuiting of the supply. So we give both polarization and depolarization the equal time. Therefore, the conduction current would be the difference between the polarization currents and the depolarization currents. If there are any residual currents that are flowing after depolarization at a particular time, the likelihood is that in this steady state current, we also have a residual current which is not due to DC conductivity, and we would like to subtract this component out from both sides, from the depolarization current as well as from the depolarization current. So the conduction current can be given as IP minus ID. From this, the DC conductivity can be calculated as sigma V D into IC kV by V, where kV is equal to pi d1 squared by 2. So this is a much more careful measurement. We are aware that we are working with very small values, and we are working with times which are not well known and which can be very large. So therefore, we should do polarization and depolarization current measurements. Now, I should also mention that since we are looking at polarization, so we are firstly calculating the measuring the conduction current. From the conduction current, obviously, we will be able to measure the resistivity or the conductivity of the material. But in this long drawn out procedure, we are also, if we wait for sufficient time, if we choose our poling times and depoling times wisely, we should be able to measure, register the entire current that flows through the circuit to establish the polarization mechanisms, similarly the depolarization mechanisms. Now, this polarization current and depolarization current measurements can be used to figure out to understand and analyze about the polarization mechanisms in the sample. And when you use this time domain measurements of the polarization and depolarization currents to calculate to obtain the different polarization mechanisms and the permittivity due to that particular polarization mechanism, because whenever you have polarization, that will reflect in permittivity. So it is possible to use the polarization and depolarization currents to calculate the permittivity of the material due to the different polarization mechanisms. It is also possible to isolate or identify which are the most important polarization mechanisms. There are a long drawn out procedure which is not very well established, which can indicate what are the most important, which are the dominant polarization mechanisms in the polarization and the depolarization current. For example, we would like to look at the polarization time, the depolarization time, the magnitudes, whether the polarization current and the depolarization currents are mirror images of each other, whether the depolarization current and the polarization current is dependent on the electric field applied. Is it dependent on the material of the electrodes? Is it dependent on the thickness of the sample? All this gives us important inputs, important insights into the kind of charge conduction that is happening during the polarization and the depolarization current. And this process of estimating the polarization mechanisms in a sample through time domain measurements of polarization current and depolarization current is called time domain spectroscopy. Time domain dielectric spectroscopy. So we have previously talked about frequency domain dielectric spectroscopy, where we plot the epsilon as a variation, we plot the variation of permittivity or polarization with frequency. Here we plot the variation of permittivity or conduction current with time. And we figure out what is the time dependence of the permittivity and the different polarization mechanisms. Ordinarily, if this time domain spectroscopy and frequency domain spectroscopy, in one case if you use a dielectric spectroscope, in one case if you use a time domain measurements, polarization and depolarization current measurements, they are completely independent set of experiments, but they should give you the same result. If you do not have a frequency dielectric spectroscope, it is possible to use the time domain spectroscopy, that is this polarization and depolarization current measurements, to obtain permittivity as a function of time and therefore permittivity as a function of frequency. That is also possible. So one method is a substitute for the other method with its inherent advantages or disadvantages, but no matter what, both should give you the same diagnosis. So this is a picture of the experimental setup that we have in the high voltage laboratory. Here you have a high voltage DC power supply, and this is the 3 electrode assembly that you see. Here is the sample, and the picoammeter we use is the 6517B electrometer, which has very high sensitivity.